One of the main reasons to use the behavior tree system is to control how the AI will make decisions. However, at the moment, our AI doesn't actually have any decisions to make. It will always do exactly the same thing, which isn't very dynamic or interesting. We'll fix that. We will give the AI the ability to decide what to do by first supplying it with relevant information from the perception system, and then make changes to the behavior tree so that the information can be used to control execution flow. We will begin by creating the new Blackboard keys so that we can store this information within the behavior tree. Open up the BT_enemy AI behavior tree. In the top right hand corner, move to the Blackboard tab. In the Blackboard tab on the left hand side, click the New Key button and select the object type. Name this new key Target Actor. In the Blackboard details panel on the right hand side, in the key rollout, expand the key type rollout. In the base class section that's revealed, change the type from object to actor. Return to the Blackboard panel and press the New Key button again, this time selecting the bool type. Name this Blackboard key Has Line of Sight. We've now added the two new keys that we need to our Blackboard. Save the behavior tree and close the window. Now that we have created the required Blackboard keys, we need to make some changes within the AI controller to update these keys based on changes within the perception system. Begin by locating AIC_third-person character from the content browser and opening it. We will start by creating a few helper functions that will make working with Blackboard keys a little easier. The first function will take an actor as an input and set a specified Blackboard key to that same actor value. In the My Blueprint panel, hit the plus icon in the function section to create a new function. Name this function Update Target Actor Key. In the Details panel, press the plus icon in the Inputs rollout to create a new input. Select Actor as the input type. Name this input Target Actor. The first step is to get the currently used Blackboard. Luckily, there is already a function within Unreal Engine to quickly do this for us. Right-click in the event graph and begin typing Get Blackboard. Select the Get Blackboard that is stored within the Variables AI section. Drag from the pin of the Blackboard component object reference and begin typing Set Value as Object. This will automatically assign this Blackboard as a target for the Set Value as Object function. The next thing we need to create is a key name that refers to a Blackboard key within the Blackboard associated with our behavior tree. We'll create a new one now by dragging out from the key name and selecting Promote to Variable. Name this new variable Target Actor Name. With the variable still selected, move to the Details panel and locate the Category section. Create a new category called Key Names by typing it into the selection box. Note that will automatically assign our new variable to the Key Names category in the My Blueprint panel. The next step will be to configure the default value for Target Actor Name. Before we can do this, we need to compile the blueprint, so do that now by pressing F7 or hitting the Compile button in the toolbar. Now, if we look in the Details panel in the default value rollout, we can see Target Actor Name currently has a default value of none. This name here needs to match exactly to the key name in our Blackboard. The safest way to do that is just to directly copy and paste the name from the source, so let's do that now. Reopen BB_enemy AI from the content browser. In the Blackboard panel, left-click on Target Actor to select it, and press F2 to rename it. This will automatically select the current text, which we can now copy by pressing Ctrl+C on the keyboard. Press Enter to leave the current key name unchanged. Return to the AI controller and ensure that Target Actor Name is still selected. Return to the Details panel and the default value rollout and select the text box. Press Ctrl+A on the keyboard to select all the text that's currently present, and press Ctrl+V to paste in the key name we copied earlier. Press Enter on the keyboard to confirm. The final thing required by the Set Value as Object function is the value that should actually be passed to the Blackboard. This is where the input we created earlier will be used. Drag from the Target Actor input to the object value of the Set Value as Object function. Drag from the execution arrow of the function into Set Value as Object. To keep things as readable as possible, I would suggest tidying up the blueprint here. The best way to do this is to add a couple of reroute nodes. You can do this by double-clicking on any section of the wire. You can then left-click and drag to reposition these. I personally like to use 2 here, just so none of the wires overlap. We're now finished with this first function. This function will make it a lot easier to update our various Blackboard values as we progress through the course. For now though, just compile and save this blueprint. The next function we'll create will set a Blackboard key that stores if the AI currently has line of sight to the player via the perception system. We'll begin by creating a new function from the My Blueprint panel as before. Call this function update has line of sight key. In the details panel, in the inputs rollout section, press the plus icon to add a new input. Confirm that the new input is of the Boolean type and name this new parameter has line of sight. Just like the previous function, we need to begin by getting the correct Blackboard. Right-click in the event graph and begin typing get Blackboard. Select the option in the Variables AI section. Drag out from the pin of this new Blackboard reference and begin typing set value as bool. Drag out from the key name variable and select promote to variable. Name this variable has line of sight name. As we'd like this to be in the same category as our previous name variable, in the My Blueprint panel, click and drag the has line of sight name into the key name section. Once again, we need to change the default value of this new name. But before we can do that, we need to compile the blueprint, so do that now. Open up our Blackboard, bb_enemy AI from the content browser. And once again, select the existing key, this time has line of sight. Press F2 to rename it, which will automatically select all of the text. Press Ctrl+C to copy this, Enter to leave the name unchanged, and then return to the event graph. Now return to the details panel, and in the default value section, update the default name by pressing Ctrl+A to select all of the existing text, Ctrl+V to paste in the new name, and Enter to confirm. Connect the execution arrow from the function to the set value as bool function. Connect the input pin has line of sight to the bool value of the set value as bool function. In exactly the same way as before, I recommend neatening up this blueprint using a few reroute nodes. We can finish up by pressing F7 or hitting the compile button in the toolbar. Now we'll return to our existing onTargetPerception updated event within our character. We will then use this event to update our newly created Blackboard keys. This means that whenever the perception status changes, the relevant Blackboard keys will also be updated. Locate AI_third-person character from the content browser and open it. Let's begin by working through each possible outcome of this event. We will start by nullifying the target actor Blackboard key when the target lost event fires. This event is currently fired 5 seconds after line of sight with the target has been lost. This represents the AI completely forgetting about the target actor and giving up. In order to access the functions that we just created, we'll first need to get a reference to our AI controller. Right-click on the event graph and begin typing getController until the function appears. This function will return a generic controller reference, but in order to reach the functions we just created, we will need to cast this generic reference specifically to our AIC_third-person character. We can do this by dragging out from the return value and begin typing cast. Select cast to AIC_third-person character. To keep everything in this graph neat and easy to read, we can convert this to a pure cast by right-clicking on the node and selecting Convert to Pure Cast. Now we can drag out from the AIC third-person character pin and begin using our functions. Drag out from the pin and begin typing update target actor key to locate our function. Connect the execution pin from the set node already connected to the target lost custom event. Connect this execution pin to our new update target actor key function. For this outcome, the desired state of the Blackboard is to leave the target actor value nullified. That is to say, we have no current target actor. For this reason, we don't need to supply any value for our function here. Let's move to the next possible outcome of this event. The nodes directly connected to the false output of this branch represent the exact moment that the actor is no longer perceived. It's at this point in the graph that we want to update the line of sight key to represent this. We'll use our function to update our hasLineOfSight key to be false. We can copy and paste the two nodes that allowed us to reach our AIC underscore third person character AI controller. We can once again drag out from the as AIC third person character pin and begin typing the name of the function we want, which in this case is update hasLineOfSight key. We can grab the execution arrow from the previous node in this section and connect up our update hasLineOfSight key. The false section of this branch occurs when the stimulus reports that the actor has not been successfully sensed. That is to say, it was previously sensed but now it is no longer visible. For that reason, we want to ensure that hasLineOfSight is not checked. We wish to update our Blackboard key to say that there is no current line of sight. The final potential outcome of this section of the graph is that precise moment when an actor is perceived by the AI character via the perception system. In this case, we will want to indicate that the AI currently has line of sight to this actor, and we will want to provide a direct reference to the perceived actor itself. We can now copy and paste all the nodes we needed to update both of these keys one more time. Begin by selecting the three nodes that allowed us to update the target actor key. Connect these to the clear and invalidate timer handle that is currently connected to the true section of the branch. In this case, we do want to supply a target actor, and luckily, we already set this up earlier. Moving over to the My Blueprint panel, locate Perceived Actor, hold down Ctrl on the keyboard, left click, and drag it into the event graph. Connect Perceived Actor to Target Actor. As a reminder, this Perceived Actor variable is something that we defined earlier in the event. We take the actor that is provided by the event itself from the perception system and set our perceived actor value to this. Finally, copy the three nodes above that we used to reach our update hasLineOfSight key function. Connect these to the previous function. Once again, this section of the branch defines the state when an actor has just been perceived by the perception system. In this case, we want to set hasLineOfSight to true, so check the box within the function. That completes everything we need to do in this section, but let's quickly review the changes we've made. We can see that this on-target perception updated event has begun to define three distinct states for the AI. The first state, following the branch when an actor is first successfully sensed, defines that exact moment that it appears visible to the AI. The second outcome, the false outcome, defines the exact moment that visibility is lost. Even though visibility is lost, we still retain the perceived actor value in the blackboard, representing a state where the AI remembers seeing something, but it's not currently visible. And finally, we have our target lost event, which is triggered 5 seconds after visibility of an actor is lost. This represents a state where the AI cannot currently see the actor it perceived, and also has generally lost interest as a period of time has passed. The important thing to note here is everything that we're doing in terms of setting Blackboard keys is purely providing information and feeding this to the behavior tree via Blackboard keys. It does not make any decisions. That is the responsibility of the behavior tree. We can compile and save this event graph as we're finished here. Now, let's return to our behavior tree and bring all of these changes together. We will use the new Blackboard keys alongside a decorator to allow the AI to decide if it should chase the player or just keep wandering randomly. Begin by opening the behavior tree asset bt_enemy_AI from the content browser. We're going to use the information now stored within the Blackboard to select between two different sequences, chasing the player or our existing random wander. This means we now need to replace the initial sequence below the root node with a selector. Delete the first sequence and drag from the root node and choose Selector from the menu. Connect this selector to our existing random wander sequence. Next, move the random wander sequence over to the right-hand side to clear some space for the sequence we are about to create. We are moving this sequence over to the right-hand side to place our new sequence on the left-hand side. This is because we want the wandering to be a lower priority than the sequence we are about to create. And as you will recall, in behavior trees, execution is from left to right. Create a new sequence by dragging out from below the new selector and selecting Sequence. change the node name in the descriptions rollout of the details panel to Chase Player. Move this new sequence over to the left-hand side to give it a bit more room. Drag out from below the Chase Player sequence and select the Move To task. For the most basic implementation of chasing the player, we simply want to move to that actor's location. We can do this by selecting the right Blackboard key in the Blackboard rollout of the Details panel. In the drop-down, select Target Actor. If you recall, Target Actor is the Blackboard key that we have been updating with the functions we've created. Next, drag out again from the Chase Player sequence to position a new node on the right-hand side of the Move To node. Select a Wait node. In the Wait rollout in the Details panel, change the wait time from 5 seconds to 1 second. It's generally a good idea to include a number of wait tasks at the end of a sequence, as it prevents the behavior tree from rapidly cycling between sequences in a way that looks unnatural. With those two nodes positioned, we have defined our basic Chase Player sequence. Because of the order of execution within a behavior tree, this new branch will always execute before the old Random Wander sequence, and currently nothing prevents this from being executed. What we need to do next is use a decorator to control the execution of this branch. It should only be allowed to execute when there is a currently set target actor. Right-click on the Chase Player sequence and select Add Decorator Blackboard. Next, select this new decorator by clicking it above the sequence node. Let's start by giving it a helpful name. Move over to the Details panel and in the description rollout, change the node name to something more helpful like, for example, is a target actor set. I personally like to frame decorator node names as questions, as that helps keep the tree readable to those unfamiliar with it, and also confirms that I'm using a decorator with purpose. If I can't name a decorator as a question, it's probably not a good decorator. With our decorator now in place, we need to correctly configure it to control the execution in the way that we want. We want the AI to execute the Chase Player sequence until it no longer has a target actor. When that happens, it should execute the Random Wander sequence. If during this sequence a target actor is set, we want to immediately abort the Random Wander sequence and begin the Chase Player sequence again. Let's start with the Blackboard key we are actually interested in. We're interested in the target actor, so we should select that from the Blackboard key drop-down in the Blackboard rollout in the Details panel. The next thing we should ask ourselves is, what do we want to know about the key? This is our key query. We only want this sequence to be executed if the target actor is set. The functions we created earlier in the AI character are such that if a target actor has been set, then the AI should be interested in pursuing that actor. Luckily, as you can see, the default option for the key query dropdown is this value of isSet. The Blackboard rollout has allowed us to define what outcome we are looking for. The flow control section above allows us to control what will happen in terms of execution flow when that defined outcome is observed. There are two options for the Notify Observer dropdown. The default option is On Result Change. This is what we want. Whenever the result of the key query changes, we will alter execution flow as described by the Observer Aborts dropdown, which we'll cover shortly. The second option is On Value Change. This would mean execution would be altered if the target actor key changed from one actor to another actor, even if the value itself was never unset. This isn't what we want. While in our example, the player is the only actor the AI will ever set as a target actor, if we later added any other actor that the AI could perceive, this decorator would modify execution flow every time the AI perceives something new. Now we have decided which type of change we're observing, we need to decide how exactly to modify execution when this occurs. That is the purpose of the Observer Aborts dropdown. The default option is not to abort anything. This would mean the tree would continue executing as normal until it tried to enter this branch again. The next option is to choose to abort self. That means aborting the sequence that this decorator is associated with. Note that when you select this, the bottom of the Details panel shows Nodes Aborted by Mode, Self, in a light green color. And the graph itself shows exactly what will be aborted in the same color for clarity. If this sequence was aborted, due to the order of execution of behavior trees, the next sequence, the Random Wander, would be executed next. This relates to the next option, lower priority. Note that the text in the lower half of the detail panel changes, as does the color highlighting the nodes that will be impacted by the change. We can see that in this instance, the lower priority random wander sequence will be aborted. Note this option would only cover some of our use cases. If the AI was currently randomly wandering and the target actor became set, random wander would be aborted and we would return to the chase player sequence. However, it's the last option that we want. We want to abort both. This means that the decorator will observe both branches and means that the AI won't ignore the player just because it's half through a move task in the random wander sequence. We want the AI to react instantly to the player. It's also important that the chase player sequence can abort itself, because as we know, after 5 seconds of not seeing the player, we will remove the target actor value. In this case, the chase player sequence being aborted represents the AI giving up and losing interest. At this point, due to the execution flow of behavior trees, it will move directly into the random wander sequence, which is exactly what we want. With our new behavior tree configured, we're now finished with the behavior tree editor. We can save the tree and close the window. In this video, we implemented the very first decision-making logic into our behavior tree. We added some blueprint script to our AI controller in order to store the information we had collected from the perception system as Blackboard keys. We then created another branch within the tree, creating a simple chase behavior using these new Blackboard keys. Finally, we used the information in the keys once more to power a Blackboard decorator. The Blackboard decorator controls the execution flow of the tree by aborting certain tasks depending on their value. We use this to make sure that the AI will wander around randomly when the player isn't visible, but will attempt to chase the player when they are visible. There is still work to do, but now the AI is using the perception system to make informed decisions on which behavior it should carry out, which is a significant step forward.